You are welcome to our presentation. This is Jared, and I'm introducing you to the topic called vectors under the theme geometry and measures. And below is our course outline or what we are going to cover in this video. So you can go through and get to know what we are going to talk about in this video or tutorial. And please, if you are not this channel, kindly subscribe, hit the notification button so that you are notified whenever I upload any video, like and share. So in this video, we are going to talk about number 1, we have the introduction to vectors. Number 2, we are going to talk about the vector representation. So like how do we represent vectors? Number 3, we shall talk about the categories, rather the classification of vectors. We shall also talk about the operations on vectors, whereby we shall talk about additional vectors, subtraction, and then scalar multiplication of vectors. We have number 5, where we are going to talk about the magnitude of vectors. We're going to cover also number 6, which reads the midpoint of a vector. Then lastly, we shall talk about the equality of vectors, or somebody can say equal vectors. So now let's try to dive in with our outline number 1, which is introduction to vectors. We are having our definition that a vector is a quantity that has both direction and magnitude or size. So we are saying that a vector quantity should have or should take on a specific direction and must have magnitude. So should have 2 of them. And you're having our examples of vector quantities. The first one, we have the forces, which by simple term we can say is a push or a pull on the body. And in here it also includes the weight, because weight is a force. Then we have another example of a vector quantity, which is displacement. And by definition, displacement is the length moved in a specified direction. Then another example is velocity, which is simply the change of displacement with time, how displacement is changing with time. Then another example of a vector quantity, we have the acceleration, which is by definition is the change of velocity with time. Then lastly, we have another example, which is momentum, and many others. That's what we are saying, and so on. The opposite of a vector quantity is a scalar quantity. And by definition, a scalar quantity is one or is a quantity with magnitude only, with size only. And we have examples. We have speed, we have distance, we have mass, volume, and many others under that category. So as we are talking of vectors, how do we represent vectors? So that means we jump over theme number 2, which talks about vector representation. And we are saying that we have part A. Graphically, we can represent a vector using a straight line and an arrow on it, as shown below. Graphically or diagrammatically, we can represent a vector by just drawing a straight line, and then we must indicate with an arrow. The arrow shows the direction of the vector, and then we are saying that the length of the straight line represents the magnitude. Remember, we have said a vector quantity must have both the magnitude and direction. So the size or the length of this straight line denotes the magnitude or the size of a vector, whereas the arrow on it indicates the direction taken by that specific vector. Then you can have part B, which is symbolic representation of vectors. So in here we use symbols. Like when we are writing, we have to use symbols. We are saying that analytically a vector is represented using a bold letter or a letter with an arrow above it or a bar above it. So here vectors are symbolically represented using a letter which can be bold or a letter with tilde. And we can see that if we have a vector which is graphically represented by this line or A, then the symbolic representation of this vector, we can say that it's simply the A with the tilde. That's why we are saying that vector OA equals to this. Then part C, specifying direction, and we are calling it sign conversion. We can see that the vector OA for this case is running from this side to this. Then we'll add this one is running from A to O. So we are saying that the vector OA, the first one here, we have Roman number 1 here, then this is Roman number 2. So we are for Roman number 1. They are saying that for vector OA, it runs from O to A. Therefore, it is given a positive sign. And you can have this. You can see that it is given a positive sign. But the vector AO, which runs in the opposite direction, that is for Roman number 2, this one, it is given a negative sign, as we can see here. So if these two vectors have the same magnitude, but they are running in opposite direction, implying that one is given a positive sign, whereas the other one is given a negative sign. That's why we are saying that specifying direction of a vector. So now we have talked about vector representation in our course outline. Let's now move on to vector classification. That's number 3. Vector classification. In here, when you are talking of vectors, we can have 3 categories. Number 1, we can have column vectors, as we are going to see or understand about it. We are going to talk about the displacement vectors and then position vectors. Let's now begin with column vectors as part A. And we are saying that under equations of a straight line, that's the first topic we covered in senior 3, book 3. You learned that a point in a plane can be specified using number pairs as x, y, where the x is the number of units along the x-axis from the origin, whereas denotes the number of units along the y-axis from the origin. And these two numbers, x and y, are called the Cartesian coordinates. So it is a point in the Cartesian plane. Therefore, it's called the Cartesian coordinate. They are called the Cartesian coordinates. The point P having x, y can be represented as, so we are saying can be represented as x, y in this form, x, y, and we are saying that this is now the column vector. So if you have the point in the form of x, y, then if it is a vector or if it is to be represented in a vector form, it's gonna be represented as a column vector, as we've seen here. Then you can have part B, which is the displacement vector. In here, we said that the vector represents motion with respect to a fixed point. And now in this diagram, we are considering point A, which is 1, 2, point B, which is at 8, 6 in the figure here. And we are saying that motion from A to B, from A here to B here, involves making 8 minus 1. In actual sense, giving us 7 steps parallel to the x-axis. So they are saying that for us to move from A to B, one has to move the steps which are 7. To move from here where we have A to point B where we have the 8. And we are saying that the steps moved are 7. How and why? We are getting the 8 where B is ending. You can see here, minus 1 where it began from at point A. Also, we are saying that 4 by 6 minus 2, giving us 4 steps parallel to the y-axis. It also moved from point A here to point B in this form, and it moved the 6 steps minus 2 to give us 4 steps. And we are saying that the displacement vector AB is thus given by, so we have AB being equal to, we have the point B, which is the 8, we have the column vector B, which is 8, 6, minus the column vector A, which is 1, 2. As we simplify, since we are subtracting, we shall have the x entities subtracting and then the y entities subtracting, them resolve separately. At the end, we are going to have the column vector as 7, 4. And this denotes the displacement vector of a point where it moves from point A to point B. You can have part C, which is the position vector. And we are saying that when the displacement is from the origin, that is at point 0, 0 or point O with coordinates 0, 0 to any point P having coordinates x, y, the corresponding vector OP is known as the position vector, and it is denoted by the OP, vector OP, which is gonna be equal to the x, y, the column vector x, y. So this is the position vector. So we have so far talked about the classification of vectors. So we have finished number 1, number 2, number 3. We are going to number 4, and we are going to talk about understand about operations performed on vectors. So for now, let's have examples. Having talked about the classification of vectors, we have our sample question. Describe the displacement made by the following vector in terms of letters given in the figure below. So we have our vectors here, and we are supposed to answer these questions. We are saying that we represent these vectors in terms of letters. Remember here, these vectors must have the arrows on them to show that they are vectors. So let's have our response. So vector A, B, we can now look at this diagram. Vector A, B. Let's look at the direction of this vector. It is from A to B with this arrow, and it is given by A, implying that vector A, B equals to A because of this direction. Then vector BA is equal to, so we can see that vector BA is the opposite of vector AB, implying that vector BA is the same as negative of vector AB, as simple as that, which is the same as the negative of A, vector A. Then we have vector DA from the diagram. Can see that vector DA is moving from this direction because of this arrow, and it's given by D. So implying that vector DA is simply the D. Then vector AD would take in opposite direction, which is this, meaning that vector AD is the negative of vector DA, implying that since vector DA is D, implying that vector AD equals to negative D, like that. Then we have BC. From the diagram, we can see that BC is in this direction before the arrow direction, and it's given by B, implying that vector BC equals to the B. Then vector CB, that's vector CB is taking on the negative, is taking on the opposite direction of the vector BC, implying that vector CB equals to the negative, because of change of direction, negative vector BC, which is the same as negative, since vector BC is B, so negative vector B. Alright, having talked about the classification of vectors, so let's now jump over operations performed on vectors, whereby we are going to talk about addition, subtraction, and scalar multiplication of vectors. That is number 4, operation on vectors. But let's begin by talking of addition of vectors. And we are saying that vectors are added by adding the respective components. And in here we are considering vectors A given by the column vector x1, y1 and vector B x2, y2. As we are performing addition on these vectors, we can see that we have added them. It simply means that we are also going to add the column vectors of them. And as we simplify this, we can see that we are adding the corresponding components. The x1 is added to x2, as you can see here, and as well the y1 is added to y2, so that we can have the vector A plus vector B equaling to this. Let's have an example here. So that given that vector A equals to 1, 5, vector B equals to negative 4, 3, and vector C equals to 9, negative 7. Then find, we are having Roman number 1, vector A plus vector B. We can have our response here. So for Roman number 1, they are asking us to get the sum of the vectors, which is going to be equal to, so we can see that vector A is 1, 5 plus our vector B, which is negative 4, 3. As we simplify this, it's the same as having 1 plus negative 4, then the 5 plus 3. As we simplify this, it is the same as having, so 1 minus 4 is negative 3, then 5 plus 3 is 8, implying that our vector A plus B equals to negative 3, 8, implying that this becomes our answer for Roman number 1. Then we can have Roman number 2, which is the vector B plus vector C. This is the same as, so we substitute. Vector B is negative 4, 3 plus vector C, which is 9, negative 7. So as we simplify, this is the same as having negative 4 plus, we are adding the respective entities or components, so plus 9, then 3 plus negative 7. So this is the same as negative 4 plus 9, we are getting a 5. Then 3 plus negative 7 is the same as having negative 4. Therefore, the sum of vector B to vector C is giving us the vector 5, negative 4. So this becomes our right answer. You can now move on to Roman number 3, which is having vector A plus vector B plus vector C. This is Roman number 3. So vector A plus vector B plus vector C. So this is the same as having, remember our vector A is 1, 5 plus our vector B, which is negative 4, 3 plus our vector C, which is 9, negative 7. We can cross check and confirm it is exactly that. So our next step is to simplify. So this is the same as, we are going to scatter out the sum of the components in the x-axis or from the x-axis. So we are going to have the 1 plus but negative 4 plus a 9. Then we are going to have 5 plus the corresponding entry there is 3 plus the corresponding entry there is negative 7. So this is the same as we simplify. 1 plus negative 4 is negative 3 plus 9. We are having a 6. Then 5 plus 3 is 8. 8 minus 7, we are getting 1, implying that therefore vector A plus vector B plus vector C equals to a 6, 1 as a column vector. Then we can have the last Roman numeral, that is Roman numeral 5 or 4. Roman numeral 4. You try out Roman numeral 4. You try out this and drop the answer in the comment section. Let's proceed to part B, where we are going to talk about vector subtraction. In the same way, we are saying that vectors are subtracted by subtracting respective components. That's to say, if you have vector A equaling to x1, y1, and vector B equal to x2, y2, then vector A minus vector B equals to x1, y1 minus the one for vector B, which is x2, y2. As we simplify that, it means that we are going to have the corresponding entry, which is x1 minus its corresponding entry, which is x2. Likewise to the y entities, where we are going to have the y1 minus y2. Let's now have example there. Given that vector A equals to 10, 3, vector B equals negative 4, 5, and vector C equaling to 2, negative 7. Then find domain number 1. We have vector A minus vector B. Let's have our response here. Domain number 1. We are having vector A minus vector B. So this is the same as, let's substitute in, vector A is given by 10, 3 minus the vector B, which is given by negative 4, 5. As we simplify, this is the same as having, we are going to subtract the corresponding entities. So we have the 10 minus 4. Then the y entities, we have 3 minus 5. You can see that here, negative and negative, we are going to have a positive, such that at the next step, as we simplify, we are going to have the 10 plus 4, giving us 14. Then 3 minus 5, giving us negative 2. Therefore, our vector A minus vector B, in this case, equals to 14, negative 2. So this becomes our right answer. Then Roman number 2. Let's try Roman number 2. So we have to find the vector B minus vector C. So this is the same as, let's substitute in, vector B equals to the negative 4, 5 minus vector C, which is equal to the 2, negative 7. As we simplify, this is the same as having negative 4 minus its corresponding component, which is a 2, then 5 minus 7. As we said, this minus and minus becomes a plus. Say that the next step we have the negative 6, that's for negative 4 minus 2. Then 5 plus 7 to have 12, implying that vector B minus vector C equals to negative 6, 12. This becomes our right answer for that case. Then Roman number 3. we are having vector A minus, open the brackets, vector B plus vector C. So let's now substitute in. We can see that vector A is 10, 3, vector B is negative 4, 5, then vector C is 2, 7. So this is the same as having a 10, 3 minus. So we have to open the big brackets here, minus vector B, which is negative 4, 5, plus vector C, which is 2, negative 7. We close the brackets. So let's now simplify this. This is the same as having, let's first deal with the brackets here, the big brackets. So we are going to have 10, 3 minus. So in here we're going to have negative 4 plus 2, giving us the negative 2. Then 5 plus, but minus 7. It's the same as having 5 minus 7, giving us still negative 2. Let's further simplify this. It's the same as having 10 minus negative 2, then 3 minus negative 2. As we simplify, we can see that this becomes a plus, and as well this becomes a plus, implying that we are going to have 10 plus 2, giving us 12, then 3 plus 2, giving us 5. Let's now conclude. Therefore, vector A minus, into brackets, vector B plus vector C, close the brackets, equals to 12, 5. So this is our right answer to Roman number 3. You try out Roman number 4 still and drop the answer in the comment section. I'll supplement on it. So now let's go to the scalar multiplication as our part C. Multiplying a vector by a scalar. What is a scalar? A scalar is just a constant. Just a constant, a value which can be 2, 3, negative, 0, and so on. And we are saying that if you have vector A having x1, y1, and k as the scalar, then k, which is the scalar, multiplied by vector A, is the same as having k multiplied by the column vector of A. So by simplifying, we shall enter the k, which is the scalar, to the corresponding entities, or to the entities, or the components. So we shall have the k multiplied by the x1, and also the scalar multiplying the y1. You have to note, it is important to take a note that when we multiply a scalar by a vector, we still obtain a vector quantity. So when a scalar or a constant multiplies a vector, still we get a vector. We have examples. Given that vector A is 10, 3, vector B is negative 4, 3, and vector C 9, negative 7. And scalars, K1 we have 2, K2 we have negative a half, and K3 we have 3 quarters. Then find, we have Roman number 1, find K1 multiplied by vector A. So we can have our responses. Let's do Roman number 1 from here. So K1 multiplied by vector A is the same as, so we are having our K1, which is 2. So it's same as having the 2 multiplied by the column vector of A, which is 10, 3. Implying that our final answer is gonna be the 2 multiplied by 10, and then 2 multiplied by 3. Implying that our K1 multiplied by vector A equals to 20, then 6. So this becomes our answer. Let's now try part B, Roman number 2. Roman number 2, we have K2 multiplied by vector B. This is the same as, so K2 is negative a half. So we substitute, that means we're going to have negative a half multiplied by vector B, which is negative 4, 3. So as we simplify this, it is the same as having negative a half multiplied by negative 4, then still negative a half multiplied by 3. As we simplify, you can see that a negative multiplied by negative shall get a positive answer. Then this 2 by 2 shall get here a 2. Then for this one, we are getting negative 3 out of 2. Therefore, K2 multiplied by vector B equals to the 2, negative 3 out of 2. This becomes our correct answer for that part. Then Roman number 3, you can have Roman number 3 here. We have K3 multiplied by vector C, which is the same as, so we can cross check. K3 is 3 quarters, so we are having 3 quarters multiplied by vector C, which is 9, negative 7. So let's simplify this. The same as 3 quarters multiplied by 9, and also 3/4 multiplied by negative 7. As we simplify, this is the same as having, so 9 times 3 is 27, but out of 4. Then 3 times negative 7, we are getting negative 21 divided by 4. And can leave it as this, since we cannot reduce it any further. Therefore, get 3 multiplied by vector C equals to 27 divided by 4, then negative 21 out of 4 as our correct answer. Wow, let's have more examples as in form of combination of all the above, whereby we are combining the scalar multiplication, addition, subtraction at the same time. So let's have our response. Roman number 1. We are given 4 multiplied by vector A plus vector B. So this is the same as having the 4 multiplied by the vector A, which is 10, 3, plus the vector B, which is negative 4, 5. Let's now simplify this. So 4 times 10, we are getting 40. 4 times 3, we are getting 12, plus negative 4, 5. As we simplify further, 40 plus negative 4 is the same as 36, then 17. Therefore, 4 multiplied by vector A added to vector B, the same as having 36, 17. This becomes our correct answer. We can now go to Roman number 2. Roman number 2, we have B, vector B minus 2 multiplied by vector C. So this is the same as, let's substitute in. Vector B is negative 4, 5, then minus the 2 multiplied by vector C, which is 2, negative 7. Let's now simplify. We have this, it's negative 4, 5, minus, so 2 multiplied by 2 is 4, then 2 multiplied by negative 7 is negative 14. As we simplify further, this is the same as having negative 4 minus 4. We are subtracting the corresponding components, then 5 minus negative 14. We see that this one is gonna become addition, so that at the next step we are having the negative 8, and then this becomes a positive 19. Therefore, vector B minus 2 multiplied by vector C equals to negative 8, 19. So this becomes our correct answer for that part. So let's have Roman number 3. Roman number 3, which is 7 multiplied by vector B minus 2C plus A. So we are having 7 multiplied by vector B minus 2C plus vector A. So this is the same as having 7 multiplied by vector B, which is negative 4, 5, minus 2 vector C, which is 2, negative 7, plus vector A, which is 10, 3. So as we simplify, 7 multiplied by negative 4 is giving us negative 28. Then 7 times 5 is giving us 35, minus 2 times 2 is 4. Then 2 times negative 7 is negative 14, plus 10, 3. So let's simplify. So this is the same as having 28, negative 28, minus 4 plus 10. We do it at once. Then 35, minus and the minus is going to become a plus, or we can have negative minus negative 14 plus 3. So you try out Roman number 4 and endeavor to drop the answer in the comment section. Let's now review the course outline. I can see that we have so far finished the operation on sides. Let's now jump over to magnitude of vectors. We are saying that if a vector A equals to xy, then magnitude of vector A is noted by the way you can see it here. So this one is read as magnitude of A, vector A, and is defined as the magnitude of vector A equals to the square root of x squared plus y squared. And we are saying that graphically, this is the same as the length of the line of vector OA from the graph below. So as we are determining the length, so that means magnitude of the vector is same as the length of that vector, or the magnitude of that vector. And it is given by, we are saying that we have the magnitude of vector A being equal to the square root of x squared plus y squared. Let's see how this one comes about. From Pythagoras theorem, we could have the length OA noted by the magnitude of vector A is obtained from this. So we are using Pythagoras theorem. So whereby if we take the square root on both sides, we are getting the plus or minus the square root of x squared plus y squared. Then we are saying that, however, since we are getting magnitude or length, and of which length has no sign, I mean it's ever positive, it implies that we are eliminating the negative, implying that we are putting the magnitude, which gives us the square root, under which we have x squared plus y squared, which is noted as the magnitude of the vector A. We have example here. We have given that OP is equal to 37 and PQ equals to 5, negative 1, where O is the origin. Determine Roman number 1, the position vector Q, the position vector Q. Then Roman number 2, the magnitude of vector OQ. So we can't have response here, our response. So Roman number 1. Remember we've been given vector PQ, then vector OP, and we are required to find vector OQ or position vector OQ. So we are going to say that from vector PQ, this is the same as having vector OQ minus vector OP. As we substituting, we've been given vector PQ as 5, negative 1. So let's substitute in. So on the left hand side we have 5, negative 1 being equal to vector OQ, which we want to obtain, minus vector OQ, which is 37. So we have 37. So let's now simplify and get OQ by making OQ the subject, implying that we are going to have, so this is the same as having vector 5, negative 1 plus, since we want to remove it from the right hand side, so we have plus 3, 7 equals to vector OQ minus the 3, 7 plus the 3, 7. So we have added it on both sides, implying that we are going to remain with OQ, vector OQ being equal to 5, negative 1 plus 3, 7. As we simplify, this is addition, so we have 5 plus 3 giving us 8, then negative 1 plus 7 giving us a 6. Therefore, vector OQ, position vector OQ equals to 8, 6. That's for Roman number 1. Then we can have Roman number 2. So they are saying that let's get the magnitude of that very vector. That's Roman number 2. The magnitude of vector OQ equals to, remember we said equals to the square root of x squared plus y squared. That's the formula. But for this case, our x equals to 8 and our y equals to 6, implying that as we are substituting in, we are going to have the square root of 8 squared plus 6 squared. This is the same as having the square root of 8 squared is the same as 64 plus 6 squared is the same as 36, but the whole of it under square root. So this is the same as having the square root of, as we sum them, we are getting 100. Then the square root of 100 is 10. So we put now units. So therefore, the magnitude of vector OQ equals to 10 units. So this becomes our answer for that Roman number 2. So in your free time, you can pause the video and try out this number. It says given that vector A is 4, 3, vector B negative 6, 8, and vector C negative 12, negative 9. Then find the magnitude of A, the magnitude of B, and then the magnitude of the sum of the two vectors A and B. So answer them, try out with them, and drop the answers in the commenting section. So now let's go on to the next one, which is about the midpoint of a vector. The midpoint of a vector, that is now number 6 in the course outline. We are saying that consider vectors OA, OB with position vectors. Vector A having x1, y1, vector B having x2, y2 respectively. Then from the graph below, we can see that the midpoint, which is point M, the midpoint of AB is given by the M, which is the average of the corresponding components of point A and point B. And since it is a point, it's in the terms of x and y. That's why we have x2 plus x1 divided by 2. Then we have a comma here, because it's a point here in the Cartesian plane. y2 plus y1 divided by 2. Why are we dividing by 2? Because we've said it is the midpoint of that line AB. Therefore, the position vector OM of the midpoint of vector AB is therefore given by the expression where we are having the OM, vector OM is equal to. So you can see that we have now changed from a point form to a vector form or column form, whereby we are having x1 plus x2 divided by 2, and then the other component y1 plus y2 divided by 2. And as we pull out the half, which is common, we are going to have x1 plus x2, then y1 plus y2 multiplied by the half. Then we separate each one of them. We are having a half multiplied by x1, y1, plus still a half multiplied by x2, y2. So here we have distributed this half to the whole of this alone, and still plus, since the plus is the same, a half multiplied by the whole of this, such that at the end we are having the expression as this. And since this x1 plus x1 y1 the same as the vector A, then we just simply substitute. So we are going to have a half multiplied by vector A plus still a half multiplied by vector B. Therefore, the midpoint of the line AB or vector AB is given by a half the sum of the vectors, the sum of the position vectors OA and OB. Let's have examples. It is given that vector A equals to 1, 5, vector B equals to negative 4, 3. Then find Roman number 1. Let's now jump over to 7, equal vectors or equality of vectors. We are saying that if a vector A is given by the column vector x1, y1, and vector B is given by x2, y2, and if these two vectors are equal, it implies that vector A equals to vector B, and therefore also the corresponding components are equal. That's why we have x1 equal to x2, and as well y1 equals to y2. We can have example here, given that vector A equals to this and vector B equals this, then solve for x and y. If vector A equals to vector B, we can have our response here. So since our vector A equals to our vector B, it implies that we are going to have the vector A, which is x plus 3, then y minus 1, being equal to the vector B, which is the 2x minus 1, then 4. So this implies that also the corresponding components are equal. What does it mean? It means that also x plus 3 equals to the 2x minus 1. So we can simplify this so that we can find the value of x. So this implies that our x plus 3, which is equal to the 2x minus 1. Let's now collect like terms by bringing the x on this side, on the left hand side. So we have x minus 2x plus 3 minus 3 equals to the 2x minus 2x minus 1, then minus 3. So negative x minus 2x, we are getting negative x. Then this cancels with that, and then also this cancels with that, so that we remain with the equal sign being equal to the negative 4. So to get the value of x, we are going to divide by negative 1 or multiply by negative 1 on both sides. So divide by negative 1, divide by negative 1, implying that our x equals to the 4. Also, so we'll do the same for the y corresponding entities. Also, the y minus 1 equals to a 4. From here, this equals to that, implying that our y minus 1 plus 1 equals to 4 plus 1. Therefore, y equals to 4 plus 1 is 5. We can conclude and say that therefore x equals to a 4 and our y equals to a 5. So this becomes our answer for that part. You try out this. They are saying that determine, given that the vectors A equals to 4 plus 2, 3m, and B equals negative m plus 8. If they are equal, then determine the values of m and q, and hence determine the magnitude of vector A. Thanks for watching. See you again in the next tutorial.